Welcome to this exercise session where we will be solving another rotating thin disk problem, but this time we will take a look at a uniform strength disk problem like the one I'm presenting here on the screen. So the problem says like this. So it says the cross-section of a turbine rotor disk is designed for uniform strength under rotational conditions. The disk is keyed to a 60 millimeter diameter shaft, at which point its thickness is a maximum. So basically what it's saying is that we have this disk here, and there is a central hole, and that hole is mounted on top of a shaft, and this is 60 millimeter diameter, which means that I can write it right now. This is 30 millimeter radius. It also says that it tapers down to a minimum thickness of, or it tapers up basically, or tapers to the top, to a minimum thickness of 10 millimeters at the outer radius of 250 millimeters. So here, what it's saying is that in the outer surface of the disk, we have a thickness of 10 millimeters. And this is happening at a radius of 250 millimeters, meaning that, not to be confused, here we talk in the inner, say, hole, there is 60 millimeters diameter, but here we're talking about radius. So this is straight away 250 millimeter radius. Where the blades are attached, if the design stress of the shaft is 250, this would be megapascals at the design speed of 12,000 RPMs. What is the required maximum thickness? Consider the density to be 7,470 kilograms per square per cubic meters. And all right, so this is very quick actually. And this is the formula that we have derived in the lectures for disks of uniform strength. Okay, so the question is, so how much is the thickness here where the disk contacts the shaft here in this case? I could solve that right away, but the only thing is that I don't know how much is this T0, because T0 is the thickness of the disk at this point here, actually. This point here is where T0 happens. And we don't know that, so we need to find that value. But fortunately, we could use certain boundary conditions to find out the value and then give answer to the question that is being asked here in this problem. So how to do it? First, we need to find out how much is T0. So T0 in here is going to be equal to what? Well, to T times the only thing, the whole kind of is pretty similar, but the only difference is that the sign changes at the top because I'm just solving for T0 like this to sigma. Yeah, but I know how to know that. Well, I know that this T0 is going to be valid across the whole radius of the disk, which means that no matter how I find the value of T0 using the values of the problem, that T0 is going to be valid all the time. So I do know that when I know that what is the angular velocity, I know what is the density, I know then what is the radius and what's the T then. Well, I know that when the radius is equals to 250 millimeters, then the thickness of the disk at that point is going to be 10 millimeters. So having this, if I input this back into this formula, then I can get the value for T0, and having the value for T0, I can get the value for the radius equal to 30, which is the one that is being asked in the problem. So it turns out to be very quick. So let's do it. So finding, let me write down finding the value for, oh, not for, but of T0. Now I can write down a little bit more information using the not boundary condition, but the condition, let's call it like that, the condition. It could be a boundary condition also. That when R equal to this 250 millimeters, so let's call it as it should be, 0.25 meters to use compatible units, then the thickness equals to 0.010 meters. Awesome. Now having that, let's substitute the values back into our equation here, or in this one here. So we're going to have that T0 equals to what? To T is 0.01 meters, E to the power of the density, which is 7470 kilograms per cubic meter, times the square of the angular velocity, but the angular velocity is given as 12,000 RPMs. I need to change that from 12,000 RPMs to radians per second. So I could say that 2 pi divided by 60. So this would cancel out. Basically, I would say this is 1 over RPM, just a unit conversion, times radians per second. I wrote down this, and this is square. And then the radius square, which is the 0.25 meter, then square. Let me write down this per. And then this is going to be over. It's going to be dividing this 2 times 250 times 10 power of 6 newtons per square meter. And let me just move because I just wrote it too close to the top here. Let me put it in here. Yeah. So these units cancel out. This one cancels out with this one. When I multiply kilograms per 1 meter over square second, it's giving me newtons. So this is going to cancel out with these newtons on the bottom. Then I have meter over cubic meter. So this is going to end up being square meter. That is going to cancel out with this one. So we don't have any dimensions in this exponent here. So this is going to be equal to what? Let's just write it down. So let's go back to GeoGebra, or let's go to GeoGebra actually to write down all of these. So GeoGebra, here we are, and let's give it names. So let's put in this case, how to call it? Well, we could write the equation again. So we're going to call that T0 like this. It's going to be equal to what? Well, it's going to be equal to one thickness here, the one that we mentioned, times e to the power of this one here. And so how much is this? So we're going to have a fraction on the top. It's going to be the density, 7470, times now this conversion of the angular velocity, 12,000 times 2 times pi divided by 60. But this is going to be square. And then this is going to multiply what 0.25 square. And this is going to be 2 times 250 times 10 to the power of 6 to make it megapascals. And then we have now that T0 equals to 0.0436 meters. So let's go back to OneNote and write it down. So T0 is, let me write down like this, T0 equals to, I should start writing these T0s like this, like in computer science or something like that, because not to mention outer here, T0. So T0 equals to 0.04368 meters, which is approximately 43.68 millimeters. So this T0 is here. Awesome. Now, to find out what's the value of the thickness, then, yeah, maybe write it down. What's the value of the thickness at radius equal to 0.03 meters? So what we need to do is to substitute how much is that using our main equation here on the top, this one here. So if we just input all the values, because I have all the ingredients to apply this equation, it would give me how much is that thickness that is being asked there. So let's do that. So let's go back to, well, let me write it down first here. So T, let me run radius equals 0.03 equals to what? To T0, but T0 is, again, 0.04368 meters. And then E, now that E, this is to the power of, well, to minus, then everything again starts here, 7470 kilograms per cubic meters. Let's relate this better. And then just let me go back quickly to GeoGebra to calculate how much is that angular velocity, because I'm interested to know just that value there. Let me see if I can copy this and put it here. Yes, I can. So it's 1,256.6 RPMs. So let's go back to OneNote. So this here is, well, it's not RPM, so sorry about that, is 1,256.64 radians per second. Per second square times the radius, that is 0.03 meters square, and divided again by 2 times the stress, 250 to the power of 6, 10 newtons per square meter. And again, I wrote it too close to the top here, so let me move it back. Maybe down there, something like this. So how much is this then? So let's go back to GeoGebra and let's find out how much is T when the radius is 0.03 meters. Let's go back to GeoGebra here. And again, let's write down the equation. So we're going to have the T0, 4368 times E, and then to the power of what? me open parentheses, and let's put the negative here. It's negative here, 7470 times 1256.64. This is angular velocity square times 0.03. This is the radius square. I want to know the thickness square. Let me take down this mouse here. Yes, and this is 2 times 250 to 10 to the power of 6. Wow, there it is. Let's go back. This is 42 millimeters, 42.76 millimeters. So let's go back to GeoGebra, to OneNote to see this. And so the answer of this, where's the cursor here? Let me write down better this because this is not legible. So T, when the radius equals to 0.03, not even meters, equals to 0.04276 meters, which is, let's put it in a fraction, 42.76 millimeters. And this is the answer, and that was it. So it's very short, very quick to solve, like this. So a brief summary, we have just one equation. The only missing unknown is the value of T0, but we can find the value of T0 because we know certain conditions along the radius, and the condition is that when the radius is 250 millimeters, the thickness is 10 millimeters. So I can use this information to find out the value of T0, and the value of T0 is a value that's not going to change along the radius or at all, for this disk, because that's the value when the radius is 0, so it's valid. It applies to that disk, in all cases. And then using this information and the other one given the problem, I can find the value of T0, which happens to be 43.68 millimeters. And this is not the final answer, but let me just put it like this. And then having found the value of T0, then we can answer the question by asking to the formula. Okay, now that we have found the value of T0, tell me the value of the thickness of the disk when the radius is 30 millimeters or 0.03 meters. And the result is 42.76 millimeters. And that's it. Most of the problems of this nature are solved in this manner. So you have a formula, and then you have certain conditions. Then what you need to do is use those conditions to find any unknowns on the form of the formulas that you're using, and then give answer to the question. And that's it. So I hope it helped, and thanks for being with me until now. We might do another one, possibly, no problem. So let's keep in touch and see you in the next video.